to discuss about the sensors. Actually, in the motors, there are having a lot of sensors, but along with that sensors, in throttle also, in electric throttle, Hall effect sensors are there. So we are going to discussing about their working performance and how they're going to giving us responses signals to the controller so they can operate at a different condition at a different condition at a different load of the motor and understand the operation of motor and controller working. And the third points where we are going to connect the function of controller with the speed approach, like when we are getting some input signal through the throttle, so the speed variations should be in the basis of factor of which parameters. So we are going to discuss all these parameters. At last, we are going to talking about different type of charging technologies, like which is already level 1, level 2, level 3. But in supportive that EVSE systems, electric vehicle supply equipments, which type of supply equipments are suitable for which type of phase power supplied, and what are their power consumptions, what are their power rating, maximum current rating. We are going to discuss all these points in today's session. So I start with the EV powertrain. In every vehicles, when we are going to start with the EV powertrain, we always flow from the powers to load, where the power will be, power source should be there, and it should keep moving towards the controller devices, and then it's going to moving towards the load part, like a motor or any subsidiary load you are going to connect it. So I'm starting with the battery pack, a battery assembly line where we are using in EV, we are using lithium-ion batteries, NMC batteries, LTO batteries, whatever the lithium chemistries batteries which we are using. We are integrated with the BMS, which is going to be monitored and which can make the SOC estimation creations for a battery management system and their variable like cell balancing techniques, OCV techniques, and UCV techniques, and the temperature analysis as well as. After then, it's going to giving power supply to the PDI, power distribution and protection unit, right? So this power distribution is going to somehow distribute the power supply to the inverters which is present under the controller. Along with that, that power distribution is giving power to the DC-DC converters. Basically, we prefer the buck converters in any of the EV segments, like a two-wheeler, three-wheeler, four-wheeler, and these are going to be chopping the frequencies of the DC current, and then we are getting a subsidiary voltages like a 12 volt, 48 volt output power supply, 32 volt power supply, which is running for a auxiliary components. So from here you can see that the DC converter is subsidiary connected with the auxiliary batteries and for the auxiliary connections. Now I'm coming towards the PDU is giving power supply to the controller, a motor controller unit, or the inverters where we are running some AC appliances, some AC compressors. So for that also we need a DC AC conversion, or depend upon the motor, which is like a permanent magnet synchronous motor, SRM motor, induction motor, or we are using a BLDC motor for a three-wheeler setup. So somehow as per the different EV segments, different motors should be selected, different torque characteristics are there for each of them. Then we are coming with the transmission part where we are coming with the differential, right? After the differential, we are moving toward to drive the wheel. So what motor is going to do, that motor, whatever the power supply they are getting from the inverter or MCU controller, they easily drive that motor to propel the wheel. Again, we having a VCU connections inside of EV powertrain. What was the role of VCU? Like vehicle controller unit coordinate the powers for the controller partial and their hot connections. Like when we are giving any acceleration, brake pedal, CAN communication, other peripheral connections, when we are going to integrate the data. So that complete command and complete acceleration input and output should be counted and listed with the VCU controller only, which is going to managing the vehicle's control completely, along with like your in four-wheelers, when we are going to operate the navigation system, vehicle telematics, it's going to be connected with the HEIM and other peripheral connections, right, which is come under the VCU command. So the power flow from the battery to the controlling system, command system, to the load, to the motor, and through the motor we are going to mechanical output. Instead of that, we need to charge the battery also. For when we are going to discharge the power from the battery, we have to also charge the battery. So we need a OBD, onboard chargers, right? If it is a DC, direct DC voltage power supply, or some external chargers, so we are going to discuss about their internal architecture in today's session as well as. So it's going to be supported for a DC fast chargers, AC chargers, level 2 chargers, or level 3 chargers. As per that, this is a bi-directional flow power should be there, and they're having a CAN communication signals also there. So from here you can see this, the dotted line indicate about the communication line. So with having an integration, make us interference connection with a charging station, we are also having a communication channel connections through the charger to EV charging stations, where we can analyze the battery, what was the condition of battery now, and while we are having a can high, can low signals, proximity sensor signals, that your charging is correctly located on the charging port or not. So these type of indication, these type of variable communication data which we are getting from the vehicle, and how much the battery is covered, how much distance. While even we are going to connect with the IoT telematics, you can also go for the subsidiary cost, right? How much cost should be examined while it the analyzing of battery, or when we are going to charge the battery for this limitation of time. So that type of communication data should be also transferred through the EV powertrain segments. So today we are going to discussing more about the controller and their internal architecture, that what are the controllers which are available for the four wheeler, three wheelers, and two wheeler, right? So I'm starting with the closed loop control system. So it will give a better idea to us that how you are going to be as a feedback control loop system in every electric vehicle. That when we are giving an electric power source supply from the battery, it's going to the power converters which are there inside the controllers, like a MOSFETs, IGBTs, transistors, and along with that, these are going to be distributed the power supply to the motor. Along with the controllers also having an input power source supplies for the accelerator and their peripheral function. Microcontrollers are also there, where the predefined algorithms are there, and as per their responses only, it's giving up gate signals, connections, pulse signals to the power converters, and according to that, power converter is going to distribute the power supply. And how the controller is getting the sensor responses in the motor, inbuilt motors, PMSM motors, uh, resolvers are there in BLDC motors, Hall effect sensors are there. These sensors are going to distribute the power, their responses to the controller, and through the controller we are getting delivering the power converter to the motor, and again then it's going to give a mechanical output connection, right? Like when we are giving an input to the electrical, we are getting the output mechanical load to propel the wheel. So that's how we call as a closed loop control system. And now I'm going to talk about different types of controller. These are the widely famous controllers which we are using, which we are seeing in many of the two-wheeler, three-wheeler, and four-wheelers vehicles, like a Reva model, Comet K, and Morris Garage, small Comet models, and all that in the four-wheeler setups, go-kart, forklift vehicles. These type of controllers which are being run on the electric vehicles, these are being controllers being used, like A5 controller, which is AC induction motor. You can see that in that they are having two input power supply connection, positive and as well as negative. Along with that, these three wires are there in common in every controller, right? These three wires, like UVW, this is one of the Curtis AC motor controller, which is widely used in the go-kart, and along with the forklift connections with the reprogrammable functions, and they're having different features. Along with that, these are the Datai controllers, where we are having a competitive with a six-phase PMSM motor and the induction motors, right? So in all of them, you will find that two input power supply sources and three external output supply source, right? Which is going to be connected to the motors, which is basically an induction motor, PMSM motor, or BLDC motor. Along with that, Kelly controllers, CY CY gold controllers which having different algorithms and all that. So these are the controllers which are present on the market, and their function was to complete command on the motor operations. And their functions in built, when we are going to see the architecturing of each of the controller, you will find the architecture is very similar to this diagram only. Okay, so you can find that these are the three wires U, V, W, which is connected with the AC motors or any PMSM motor and all that, along with the resolver, Hall effect sensor responses wire connections, and B positive and B negative, the battery power source which we are giving to run the motor, right? In hence, after that, we are having a lot of wires where we are giving the input functions, auxiliary output connections, communication channel connections, specification mode wires, or specific features like if they are having a suitable for a motor sensors, then we are integrated with that. There are different modes for a forward, reverse controlling. These are the controllers which are highly based controlled configurations controller which we are using for electric vehicles, so we'll get a efficient output, right? So let's to look on the operations. For that operation, I have taken one of the example of BLDC motor controller. So you can see that in that they are using a lot of MOSFETs. So you can consider it as a DC current power supply, DC power source, positive and negative connection. And then we are giving a power supply controller output as a UVW, or if you are using PMSM motor or phase sequence or BLDC motor, you will the wire should be in the yellow, green, and blue, right? So you can see that the MOSFETs, the IGBTs, they are having a 24 tubulars, they are having a 32 tubulars. Means that the set of numbers, the set of number of MOSFETs which are inside that, like how many frequency devices are there inside that. That was the meaning of 32 tubular or 42 tubular controllers, right? So what they are going to do that, these are the power converters devices are there. Here the controller, microcontroller responses. First, it's giving a once power supply to the motor. It's also giving a power supply source to the Hall effect sensor, right? These are the wire for the Hall effect sensors. Five. These two wires are giving a power supply to the Hall effect sensor, which is present inside the motor. And again, instead of that, we are getting a responses power supply from the controller, right? In a UVW, so we can detect the position of rotor, and through as per that position of the motor, we are giving a power supply to these diagonal switches controlling devices which are having a high frequency, right? And along with that, these are also converging the power supply source. It's always been not been flow in the forward direction only, it will also flow in the reverse direction for the different paths, and it can create a magnetic pole as a south pole as well as a negative pole in the BLDC motors. So this is a complete commanding operation which is inside the controller, right? So as we talked about BLDC motors, the BLDC motors are brushless DC motors which having a highly advanced motor which having a high initial torque and high running torque, as well as these are the motor which can't run without the controllers. So we need a inverter connections, we need a AC DC conversion. It's all these motors are working on the trapezoidal wave signals which is coming output from the controller. So you can see that the wires that we are getting from the command in the point of view. And first of all, I'm saying that it's a both are the BLDC motors. You can from the architecturing you can understand that which is the center type motor and which is the hub motor, right? So from the internal architecturing you can understand these was the rotor position and this was a stator part. So it's a mid runner motor or is a center type BLDC motor. This was the motor where the in center type was a stator part and the external part was a rotator part. So we call as a hub motor system, where you can analyze with the center type BLDC motor. You can see that when we are getting a three phase power supply, it will create it. Two of them are being energized and one of them are in off condition, right? And simultaneously these two been in charge and this was in off condition. So according to that, when we also know that a DC power supply is never been in the three phase power supply, We always we always getting a positive and negative terminal power source from the DC batteries, right? So how we are going to distribute them in the three phase wiring connection? So what we are going in the three of them, two are in always in the energized condition and one is in the off condition, right? So vice versa, simultaneously it will be swapping between of them. Along with that swapping, you can see this, I am taking one of the pole, you can see that the direction of the magnet should be also changed. Now in that they are having a south pole and this one is a north pole, but again the swapping when come back, you can see that this was a north pole and this was a south pole. So high efficiently to run that motor, the when to come in the forward connection, when to turn on the power supply, when to flip the power supply, all these are getting responses with the help of hall effect sensors which are present inside this. And in the motor which we hall effect sensor we use is called bipolar hall effect sensors. And these bipolar hall effect sensors are capable to detect the position for a north field as well as a south magnetic field, and as per that only they are giving to the command to the controller. And each BLDC motors having three sensors, three bipolar hall effect sensors, right? In the case of hub motor, you can see that their external architecturing was like for a slots of magnets are there inside the rotor only, and in the stator part it was creating a south pole north pole as per the power delivered in the between of the controller operations as I shown you earlier. So you can see that at the two at of cases these two been are energized and one of them are in the off condition. Like simultaneously the motor is getting the power supply and as per that it will complete the rotation of 360-degree, right? So now I'm going to start with the the two-wheeler, three-wheeler concept where we having a CV Gold controller, which how they're operating. Now I'm going to looking on the four-wheelers motors like a huge golf cart motors, three-phase induction motors, PMSM motor, six-phase motors, where you can find that UVW power supply connections and their controller function. So in that, some of them case MOSFETs are there, some of them case IGBTs are there, right? So here we have seen that we are giving a power supply to the EV battery, through the EV battery to the controller, through the controller inverter. So this was a B1, B plus and B minus. Along with that, we are getting output power supply where we are having a VUW. And in the VUW, I can also show the complete operation, right? And these in IGBTs are also being connected and giving a power supply with the in the diagonal form to giving a utility power supply to the V or this converter is going to giving a power supply source for the U calculations. Along with that, when we are getting a power supply from the battery, we are giving to the controller. We are also giving some power supply to the compressor motor assemblies, like if we are having any AC supply or power distribution converters, when DC to DC converters which are having a ECU connections which are having a low rating of components, so we are giving some external power supply from there also. Like in the controller also we are getting CAN communication wires, along with that battery meter wires, hall effect sensor wires, crucial control wires, vehicle telematic wires, along with that navigation system which is come under the telematics only, forward reverse functioning, controlling functions, step index functions, and all these type of functions. Lot of wires are coming, it's near about 35 wires, and they are having a different modes of wire also. Like when we are going for a speed control mechanism, speed control triggering purpose, like a MPT controllers which we are using. So in that, how the powers should be reaches to the each of controller, we are going to see that, right? So how the power was delivered by the permanent magnet synchronous motor in the UVW inside the motor architecture. Through this animation, you can understand that in this condition, the first condition where the motor internal rotor is having or created a north pole and south pole. Along with that, these are U is going to be connected, creating a north pole, and south B is creating a south pole, right? In the second point of view, when the magnet is having a connect with the north south in the saturation, you can see that these is completely going to be south direction, so the it will create a more attraction for the north magnet, right? Along with that, when again it's going to sweep, that you can see that this is completely energized and this was in the off condition. So according to that, according to that phenomena of the motor only, that these motors are going to be working, and these power supply, when to give the power supply, when to not give the power supply, how much frequency which we are getting, at the what frequency is in been run. So complete algorithm and complete analyzation was done inside the motor only, right? And their complete operations. So as I told that we are getting a responses from the bipolar Hall effect sensors, linear Hall effect sensors. So we are giving in a two-wheeler, three-wheeler, basically electric throttles which we are using to giving a power supply signals, right? So in the integrated circuit of transition magnetic field, how these Hall effect sensors are being working, and how we are getting our responses from any of the sensors. Simultaneously, they are having a transmitter and the receivers are there to get the output receiving, to get the output from the sensors, right? So Hall effect sensors are will be voltage induced on the conducted of magnetic field, right? In the nearby magnetic should be there, or the magnetic field was there, as per that is going to be give some saturation in their voltages, and they're giving a maximum voltage up to 4.56, and their input, the sensors having an input voltage near about 5.5 to 6 volt only, right? So these are the Hall effect sensors. In this Hall effect sensor, these data which is mainly you can get in the data sheet of the complete specification of the 49E, right? Along with that, this animation will show you somehow integral working of the 49 when you're using a semiconductor device which is having a Hall effect sensors working to changes the voltage placed in the magnetic field, right? If we make a magnetic field near to the sensor, you can see that the complete saturation, and we are getting some fluctuation, and we are getting some output voltage in the receiver wire, and from that we are getting some responses. So these are the linear Hall effect sensors which are present inside the throttle, electric throttle, right? So this is one of the picture of electric throttle. Here you can see that we having one arc magnet inside the electric throttle, right? Along with that, we having spring inside this, and then this coupler was there, and inside that they are having a Hall effect sensor, linear Hall effect sensor, and it is giving a three wire connections, two for the power supply source, and one is getting we are getting a output response from the sensor when it's coming near contact with a strong magnetic field. These are the magnets which is nickel cadmium magnets are there, okay, and one of the poles like a strong magnetic field, and one is near about they having a low magnetic fields like a north pole, south poles, but it's not going to detect the north pole and south pole, it's just going to detect the highly magnetic field, right? If we are going to go for the highly magnetic field area, you will find that your the output voltages which we are getting from the sensor, it's more higher, right? So you can see this. I've taken a one animation to understand this, how the Hall effect sensor is going to be worked. You can see that when it's coming to the near to the Hall effect sensor, its the voltage should be increases, right? So we are giving an input power supply to the throttle, and we are getting an output power supply as a waveform responses. And this response is going to giving to the controller, and that controller is as per that only they are giving the voltage. It increase the voltage, current, and frequency which is delivered by the power electronic converters. So we are giving the input power supply from the battery through the BMS to the controller. Along with that, we are giving some manual responses. As per that only the vehicle is going to be run, right? So these type of sensors which are used in the electric throttle, along with that electric throttle for a two-wheeler, for a three-wheelers, and for which type of the MPT controllers which we are using. In MP controllers we are having a potentiometer. In that we don't having this type of Hall effect sensors, but no rheostats and potentiometers are there in the electric throttles which we are using nowadays in a two-wheeler and three-wheeler, right? So I'm coming toward the bipolar Hall effect sensors. In the bipolar Hall effect sensors, is a sensor which is using the BLDC motor to detect the position of rotor. And these are 8 pole motors with having a, not is a 8 poles, it's depend upon the speed of the motor and architecture of motor. But yeah, you can say that it's a three-phase winding motors which having a three bipolar latching Hall effect sensor. These bipolar latching Hall effect sensors are actively Hall effect sensors which are having a uh, complete inspection and detect the position of rotor for a north as well as a south direction, right? So you can see that in the inbuilt architecturing of the motor, you will find these type of sensors. Here we are in these three, we are giving a power supply source to each of the sensors, right? Positive and negative, and through each of the connection, you can find that blue wire, green wire, and yellow wire. It's giving to connecting, getting the data where the strong magnetic field was there, where the north magnet was there, where the south magnet. As per the responses, it will create a waveform like this signals which we are getting to the and to the we are sending these signal to the controller, and through that controller with whatever the controller out performance that VCU is giving, as per that only the operation of motor, and we are getting a 120 degree, 120 degree, and 120 degree. So we are getting a complete 360 degree rotation of the motor in the nanoseconds, right? So what, how we can differentiate that a bipolar and linear Hall effect sensors? These two sensors is widely used in the electric vehicles. One sensors, linear Hall effect sensors, which are being used in the electric throttle for acceleration of the motor, right? And bipolar Hall effect sensors, which is inside the motor, which is going to detect the position of motor, and each BLDC motors having three sensors, right? So second differentiate point was that like a linear Hall effect sensors only measure the angles, right? Displacement in the angle, where the bipolar sensors are responses the both north and south pole magnetic allow the wider area of measurement, right? It's not only for some particular angle of rotation, so they are getting a response. So there are huge difference between a bipolar and linear Hall effect sensors responses, right? Now coming to the one of EV motor speed control approaches. In the EV motor speed control approaches, they are having AC induction motors, AC BLDC motors. These are but wide approaches which we are using is a vector quantity variable frequency devices which we have uses is a vector quantity where FOC techniques are there. Field oriented control and DTC where the direct torque control, right? So in FOC, we are basically uses for the induction motor, PMSM motors, or when we are going for a frequencies enhance and the torque speed range of the vehicle. And when we are talking about DTC, we are using BLDC motor, induction motors, and PMSM motors are suitable, but we have recordedly fluctuate the value of current and motor and the magnetic flux based on the motor's responses, right? So these type of responses while we are using for the speed approach when we are giving the initial throttle responses to the controller. So that's how when we are going to talking about the operation of EV powertrain, insightful complete operation, how the motor is getting a power supply and then how it's going to distribute that power supply to the motor as per their power rating and as per their architecture. Like even we are having a three-phase induction motor, AC induction motor, so UVW connections, resolver sensors are there, CT responses which we are getting. Along with that, when we are talking about BLDC motor, BMS, permanent magnet synchronous motor, you will find that Hall effect sensors are there. Along with that, these controllers where the throttles are there, that throttle is also one of the sensor only where we are getting the data, where we are getting the, sorry, we are not getting data, we are getting analog signals from the Hall effect sensors. And through, as per that only, we are going to enhance the speed of the motor or enhance the speed of the vehicle, right? So as a powertrain component where power is going to sending to the controller, and then controller is going to deliver the power to the motor, so to propel the wheel. Along with that, second EV powertrain concept was that always it's getting been charged. So how they are charged in the charging electric vehicles? When we are going to plug in electric vehicles, the first of the things which come in our mind that it should be a DC charger, AC chargers, their responses, their fluctuations, and their advantage, disadvantage, infrastructure development, these type of things which we are coming inside our mind. So we are familiar with the types of charger, level 1, level 2, level 3 chargers, where we have categorized them in AC power charges, DC power charges, in AC also having a low volt chargers, level 1 chargers, level 2 chargers which are having a high volt charger as compared to level 1, and at level 3 chargers where we call as a DC fast chargers, which is going to deliver a huge power supply source to the DC, to the battery, and it will be a fast charger also, right? So in every charging stations we will find this type of chargers. Along with that, we can categorize them into on-board charger, off-board chargers. But still, when we are talking about the EVSE, electric vehicle supply equipments, we are talking about charging infrastructure. About out from the electric vehicle, we are going to charge with the connectors, the supply equipments which we needed to give the power supply source to charge the vehicle. Then only it's capable to deliver the through the OBD, it's going to capable to deliver the power supply to the battery, and then battery is going to help to discharge. At the time of discharging from battery, is going to propel the wheel, right? So we are going to see that we have always go for the RCD chargers, which are the chargers which we are getting also value from the vehicles for a two-wheeler, for four-wheeler. Along with that, home in charging sockets are required, plug, controller, charging gun. In the term of charging guns, when the charger, with the help of charger, every vehicle's having different type of charging socket as per the company OEMs, as per the constructions, or nowadays some universal chargers are also coming, right? So along with that, we are looking for the charging port connections which are there inside the vehicle, and we can operate them for like when we prefer for a level 1 chargers, level 2 chargers, it will take a huge time to charge the vehicle, right? So coming to the charging stations, along with that, charging connectors, electric vehicle supply equipments, the charging standards which we are using, right? So the voltage and the power, as per that, we have classified their standards and as per their characters. SAE chargers, IEC chargers, international electrochemicals connector chargers, along with the AC charger, DC chargers, and type 1, type 2 chargers, CCS chargers, where which are compatible for AC chargers as well as the DC chargers. Along with that, there are variations of chargers which are being there, right? In that case, they are going to be compatible with each of chargers. We are having their different parameters, different maximum rating, different voltage fluctuation, power consumption of the vehicles, right? So I'm starting with the type 1 AC connectors, which we also called SAEJ1172 chargers. And these chargers are being supported for a single phase power supply, right? And these are having a rating of 120 volt. So along with that, the output power is capable for a two-wheeler, for three-wheelers, power supply source. Type 2 AC chargers, where IEC standard, which we are using for a single phase supply as well as three-phase power supply source, right? So for a three phase, for single phase power supply, it's been suitable. When we are go for a single phase supply, it's will getting a 240 volt and near about 80 ampere rating, maximum current up to 80 ampere. When we are going for a three phase connection, we are getting a 500 volt and near about its rating, maximum rating up to 63 ampere, right? So these type of chargers which we are having a connector plugs. And now we are going to deep discussions while to which are the ports which we are using. Like we can see that in every gun chargers, they are having lot of slots. There, some of them are having only three, some of them are only having five, some of them are having eight. So what are their pins allocated to each of them? In upcoming slides, we are going to discuss that, right? So I'm starting with the first DC connectors. In AC, we have covered type 1, type 2, which we called SAE, IC, J1172 chargers, right? Now, when we are going to DC chargers, DC connectors, we will find that CHAdeMO, Tesla connectors, GBT chargers, CCS chargers, which is CC1 and CCS2, right? So these chargers are suitable for some of them, like CHAdeMO is having a DC fast charger suitable. Tesla connectors having some maximum priority value, the CAN communication, their security levels, and as per that, along with that, GBT Chinese chargers, which are supportable for both AC as well as DC. CSS chargers are also there, which is supportable for AC plus DC and plus for single phase supply and three phase supply. So as per your charger supportable, as per the charging station which we are there, and their the supporting of vehicle, they are coming inside their architecturing point of view and their power analog connections, right? So I'm starting with the AC first charger. In AC EVST, where we have called SAE J1772. In this, they're having multiple pins. These are the single phase AC chargers, and these AC single phase chargers, where you can see that L1 and N is a phase line 1, and N connection, N denote for the neutral power connection. Then we are coming with the earthing wire, P wire, which is giving the power supply source of for earth grounding point. Along with that, proximity detection, when we are going to connect your charger. So when we are getting a responses from the proximity detection, then only we are charging the power supply, trigger the charging station to start delivering a huge power to the chargers. So these are being used for the proximity sensors. Along with that, CP chargers. CP denotes with the control pins, valid to enable the control functions for a communication channels. Some analog responses are being there. Through then they can analyze the data of your vehicle, and as per that only how much power was being stored in the duration of 3 hour for 4 hour. Then only it's been help you to generate the bill, right? Second types of charger, which is type 2, right? In this type 2 charger, this is very similar to SAE chargers. Proximity sensors, pilot wires are there. Proximity pilot wires are there, which is going to detect the position for the connectors of the charger. Control pilots are there, where we are having a communication channel interference. Protections, earthing wires are there. Along with that, a three-phase connection and a neutral wires are there, which is having a suitable for a bulk power supply. It's having near about 500 volt power supply, and it can deliver up to 80 ampere power source in AC mode of chargers. Now coming to the DC modes of chargers. In DC modes of charger is a Tesla chargers, which we are uses suitable for the Tesla vehicles, and these are like supportable for AC as well as DC, right? In this also you will find that communication wires are two communications wire, and these two communication wires are working as a CAN high and CAN low signals, right? For a CAN high and CAN low signals, along with that a ground connection was also there. And for AC, the connectors are being handled of single phase power supply, which is having up to 240 volt and maximum rating up to 17.2 kilowatt, right? Along with that, when we are talking about DC chargers, it will giving up to 250 volt up to 500 volt and maximum rating up to 250 kilowatt, right? So these type of AC charger, DC chargers, as per that, only the vehicles is going to be initially fast charging when we are going for a DC chargers. Along with that, the battery pack we have selected. What was the C rate of the battery? Was supportable for a 2C, for 3C, for 4C or not. According to that also, it's going to be deliver the power supply. So that type of configurations, functions, architecturings are there in the charging stations also. Now coming to the CHAdeMO, right? Charge, demove, where we having a CHAdeMO names come from this. this DC fast charging chargers. Along with that, you can find that a ground wire, charging enable disable indication wire, charge to stop the charge and disconnect the power supply, can high, can low wires are there. Protection earthing wire, pilot wires. These are the basics functions for like communication wire to detect the position of wire. But when we are talking about can high, can low means control area network high language wire, and low, these pins are going to transmit and receive the communication signals. So whatever the communication between the charging station and your vehicle can be possible through these points of the chargers connector only, right? And C1 and C2. These C1 and C2 control signal 1 and control signal 2 wires also are receiving functional special functions cases may be implemented for a future extension scope or when they are having a subsidiary features. So they are capable to handle these type of things, right? So they can integrate it with the future extension for future, like when we are going for any energy consumption, when we are going for a IoT devising, when we are going for a navigation, that from to get their competitive responses, we can provide some in we can use that interference power supply source for that connections, right? Along with that, a third terms like I have discussed about the AC connectors, DC connectors, and the CSS connectors. CCS connectors mean a combo combined charging systems. They are having a one and two type. These combos CSS chargers are supportable both AC as well as DC, but their combo one and combo two types are differentiate, while the single phase power supply and three phase power supply in the DC connections. So you can find that for a DC power supply, we are using the down terms like DC plus, DC minus in both of the chargers. See, in a combo one and combo two type of chargers. Along with that, you can see that CP wire, uh, controlling pins wire, along with the proximity presences of wire pins, along with that P for a protection earthing wire, and CCS combinations where line and three phase connections wire. You can differentiate with the L1, L2, and L3 with the three phase connections, right? So these type of chargers are there in the market, and along with that, these type of chargers, some of the chargers which are using in the European and the Japan's market, but in the Japan countries, but some of them we don't have that much vehicles configurations, interference or charging infrastructures also not there. To resolve that solution, nowadays companies are with coming with a universal chargers that which is supportable for a four wheeler also. That you are having a RCD chargers, you can just go and plug your vehicle like for a 15 ampere socket or for a bulk heavy high voltage power supply sockets. You have to connect them. You can access them through where the IoT cloud system, their server, or for the RFID, for the manual access, and these type of parameters being there. Suppose let's when we are talking to a charging, it will take like how much time should be calculated while to charge any EV vehicles, how much time it will take to charge that vehicle. That was a subsidiary questions which are coming while to when we are going to purchase this vehicle, any vehicle. So when we are talking to estimation of the power, so you can take one approximation calculation from this. So for that you need a battery capacity. What was the total amount of charge the battery will be required? Is actually having and how much charge power we are giving to the battery. So as we know that P is equal to VI, power into voltage into current, along with that charge time, when we are categorizing with them, so we have to just describe the battery capacity into power and along with the power factor. When we are using AC, we will take a 0.8, and when we are taking a 0.9 when we are using the DC chargers connections, right? So I've taken one of the example, Nexon EV Max. Let's take an example of Nexon EV Max. It's having a 40.5 kilowatt battery pack. Means is near about 42 kilowatt in the real life, but I've taken example of 40.5 kilowatt battery pack, and it comes with a standard of when we are going for a AC chargers, it's coming with the 3.3 kilowatt AC chargers and the premium chargers, which are level 2 chargers of AC, which is 7.2 kilowatt charger capacities, right? The powers which been there. So calculate these two cases. In that, I have get that by applying this formula, charging time is equal to battery capacity by battery charger. We can see that when we have uses a 3.3 kilowatt chargers, we have just given a battery capacity 40.5 kilowatt, and with the help of the power which we are giving 3.3 kilowatt. So after applying a cost in the AC power factor 0.8, we are getting a 12 hours to charge this complete battery pack, right? And the charging of the premium of 7.2 kilowatt, the power will be increases in this which we are giving to charge the battery. You can see that it will take only near about 5 to 6 hours to charge your complete vehicle. So like that, according to the power we are increasing value the chargers, it can enhance the or it can decrease the charging time of the vehicle, right? So this is a one of the EVST supply equipments which we are have seen in nowadays in the universal way of the market. So you can see that this is the one of the charging infrastructure for a level 1 and level 2 chargers, and this is having a rating of 9.9 kilowatt, and this having a three sockets, and these each are having a 16 ampere sockets, and it can be accessible by manual RFID card or through the app through the server also, right? So now in the first case, you can first step you can see that we didn't connected any of the power supply source. So that was the initial condition. When I am going to start the power supply connection, so after that it will you will need to access through the RFID or through manual operation, and after that you can see that when the battery is going to be connected, charging connections should be there from the chargers. It's going to charge the battery. So in that connections type, universal chargers are coming nowadays in market to connect any of the vehicle for level 2 level for two-wheeler segments, three-wheeler segments, or four-wheeler segments to charge your vehicles, right? So let's talk about when we are talking about internal architecturing of the each of the equipments. We are talked about EVSD supply equipments of 9.9 kilowatt. So you can see that one of the touch screen panel where three scanners were to integrated with the IoT servers app. Along with that, manual OTP was there and RFID access was there. And what was the internal architecturing was there. So I'm not explaining the complete circuit, but I'm guiding you somehow that what are the essential components that we are there inside the charging infrastructure. The chargers we are having a first we are getting a power supply from a back end power supply, input power supply from outer three phase connection, earthing wire and negative wire, three phase MCBs are there, right? After then they are having a voltage distributor connections. After that we having a auto restart connection. These are the RLC circuits, IC circuits which been giving a deliver power supply to the this microcontroller conversions, and along with that these are the ELCB when the extreme power was being delivered or any earth leakage fault, right? So they are having a tester tips when we are going to demonstrate them, when we are going to use that it's working or not, that if they are use the ELCB, they use the time delay relays, and according to that they are giving subsidiary three, they use three of pairs because they are being delivered the power supply to the each of the sockets, right? And along with that they are also having a configuration integration connection for the RFID access, and this microcontroller is going to be suitable for to running that IoT device and complete configurations. You can see that a GSM module or EPSM modules are also there, right, to connect with the server or to it will help you to the operator to define each of the cases. So that's how the internal architecture of the complete charging station of electric vehicle service station, EVST electric vehicle supply equipment systems, right? So that's how that's in from my side. If you have any queries regarding this, any of the operations, if you want to know, you can ask the questions now.
If you have any doubt regarding this, you can ask from our expert.
Do you have any queries regarding any of the topic? So we will discuss. I'm opening the door for any questions, any query regarding this today's presentation. So I hope you have enjoyed this session. So the concerned team take the call from here.
Thanks for hosting the webinar. Your expertise and insight were invaluable for our learners. I would like to take the opportunity to introduce our company ISI India product and services that we offer in EV technology with small video. So kindly have a look on video.
As we are living in the fast changing world of electric vehicles, ISA India is leading a tech organization, paving the way for innovation and revolutionizing the ecosystem. It is bridging the gap between industry and academia and bringing all the stakeholders to the same table. From 2013, our parent organization has been tirelessly working to create an ecosystem for skill development, research, innovation, and entrepreneurship in the electric vehicle industry. Through CSR skill development and partnership with GIZ, Tata Technologies, Bharat Crop Science, Kalika Industries, Chalna Jan Seva, Masiya, IPCA Laboratories, etc. And with national and international e-mobility events such as Electric Solar Vehicle Championship, Formula Imperial, Indian Karting Race, e-bike design challenge, we have provided a platform for over 3 lakh students from more than 750 colleges and universities to come up with the innovative projects. In addition to this, we are offering various skill development programs, faculty development programs, corporate trainings, and spectrum of courses with duration from 9 to 12 months with live and recorded interactive classes, with the added flexibility of paying after course completion. For our contribution towards building sustainable way forward in EV, we have got recognitions such as the National Youth Award from Ministry of Youth Affairs, Government of India, Titans of Technology Award, EDN Star Award from Earth Day Network USA, and the Social Entrepreneurship Award. And we have also joined hands with Automotive Skill Development Council, All India Council for Technical Education, National Skill Development Corporation, Ministry of New and Renewable Energy, and various automotive industries, which validate our global impact and commitment towards excellence. We are now a global partner for talent nurturing in the automotive industry. We are fostering the youths for the global EV market and have recently joined forces with partners in Malaysia, Indonesia, and South Africa. According to the economic survey, in India, the market for electric vehicle is expected to grow really fast, about 49% every year from 2022 to 2030. This means we could see 10 million electric vehicles sold every year, and which led to 50 million direct and indirect jobs by 2030. We are committed to sustainable mobility solutions and our industry aligned programs cater academia, industry, and government sectors. Our expertise in the industry has led us to design cutting edge technological solutions for the growing electric vehicle industry. We promote project based learning, hands on training, skill development initiatives, vocational training, research, entrepreneurship, public private partnerships, awareness, and outreach programs. Our state of the art facility, the Center of Excellence for Electric Vehicle, is dedicated to spreading the word about electric vehicles by facilitation of technological advanced solutions. EV Tech Lab. It's a high-tech lab designed for students studying engineering, ITI, and polytechnic students getting job training. Think of it as a space where creativity meets actual hardware solutions. People here get to dive deep into the physical part that make electric vehicle work. This model is also helping our partners for community skilling of various job roles such as electric vehicle technician, vehicle assembly operator, charging station operator and technician, and workforce for electric vehicle powertrain, battery and BMS maintenance, etc. Second model, that is our Center of Excellence for Electric Vehicle. It's a combination of labs and offering both hardware and software solutions, under which we have established end-to-end solutions for electric and hybrid vehicle design, powertrain, battery and BMS, EV charging, IoT for experimental learning, testing and prototyping. The solution we are providing is unique and help our learners for upskilling, research by getting experimental data and plotting graphs. Our goal is to impart industrial knowledge by establishing pioneering center of excellence. These centers, developed in collaboration with universities, industry partners, and government entities. Our COEs provide integration of EV curriculum in BTech, MTech, and other academia programs. Research and vocational NSQF courses align with the national education policy. Plus, our COEs also support the startup ecosystem by providing facilities for design, prototyping, and product testing. Our labs are making difference. We have established several labs across strategic locations with all kind of stakeholders like industry, Hero Motocorp, with Government of Kerala in partnership with MG Motors at two locations, IIT Mandi, private universities like SRMU, Calcutta University, Sharda Universities, an NGO with Govardhaniko Village by ISKCON Temple, and various top universities and institutes across India. Our commitment to excellence is unwavering, and by 2025, we aim to establish over 250 plus center of excellence worldwide. With India rapidly moving toward an electric-only future, ISA India is well positioned to develop the workforce prepared for the international arena. Join us on this electrifying journey towards a sustainable and innovative future.
Thanks for watching the video patiently. So don't miss out on this opportunity to discover the endless possibilities of EV. So any of you want to enroll in this course, kindly send us inquiry through a QR code displayed on your screen and take your first step towards a more sustainable and exciting future. And also we are having the exciting offer on the hello. Thank you.
If you have any query regarding the courses for BMS battery, you can scan this QR code and our executive will contact you shortly. For certificate issue, like if you didn't get the last webinar certificate, I have mentioned an email on the chat. Please email us about the certificate issues. If you have any query regarding the course, if you want to course for a BMS, battery, motor, we can guide you much better. Our executive will contact you shortly. Scan this QR code. Thank you for attending this webinar. Hope you understand all your queries. and wonderful session. Thank you. Thank you for joining, everyone. Don't forget to fill the feedback form which is given in the chat box.